Alright, hello and welcome back. I'm just process of designing my XOR gates and in preparation for a binary adder. So that's a much simpler XOR gate than this one over here. So this one has, the problem is I want one that's plan form that's in like a 2D, on 2D plane, right? This is obviously 3D, the bridge. Topology of it means you have to have one signal coming over the other. But here's the thing. This format has only essentially 2 transistors in it, whereas this format has 1, 2, 3, 4, 5 essentially. So obviously the planiform version is much more inefficient. See, I want a planform one because I want to stack them up into like a tower, to a stack of. See what I've done with the memory over here. This is the RAM. And obviously I've got like 16 MOSFETs. Get it? MOSFETs. And on each one, obviously, there's a 1 gap between each one. So since it's working in 16 bits, it works out nicely to have like a layer, essentially to have 2 blocks per bit. So it stacks up nicely, basically. Which is why I want an XOR gate that's planform. But I think the trade-off in terms of, because each one of these little Minecraft repeated gate things adds a tick of delay. I think it's going to be much better to go with one of these. And what I can do is I can alternate the so I can essentially have one layer like this, and then the next layer will be juxtaposed to the side, and the next layer will be back over on this side, so it'll alternate in a zigzag. That way it'll still be spatially efficient. So basically that's the XOR gate. Now I'm going to include the XOR gate into a half adder, because the idea is to make the binary adder, because I'm working on the CPU. The first thing I'm going to build is an additions instruction set. Additions. Oh, excuse me. An addition instruction code, or operator code. So I'm just gonna build an experimental MOSFET here. So XOR, we're going to have 2 guys coming in. Yes. So I think this gets switched off if that is on. So it should be like that. Just check that that works. Yes, that works correctly, and then you go up like this. I know how to do this. Put some glass there. And some, yes. Now this should work. And what you want to do is have a relay here, or rather a repeater. If you ever see me fumbling for the right key, it's because I've got a trash keyboard. So repeater here. That's not what you want to see. Oh yes, naturally. That's what you want to see. So that's a reasonably efficient XOR gate. Now to make it an overflow bit, so you'll have this essentially, and if this is on, that cuts this off. So basically that's the overflow bit. This is going to be the regular bit. But to make this properly work, it needs to receive an overflow bit from a. So it needs essentially 3 inputs. So I think if you have an input here, right, so if it receives a 1 from the previous input, you want that to So you want there to be let's say you have 3 ones, you want there to be one on the input and then one on the output on the overflow. If you have 1 1 and so if you have 2 ones, you want there to be one on the you either want there to be one in the overflow. No, you want there to be one in the overflow. So in reality, what you want is something attached here. So we'll say that this is the overflow bit from the lower order binary adder. To put a repeater there to stop back propagation. That's on. So if that's on and that's also on, that doesn't matter. Well, no, because if that's on and that's also on, you want it to be. You essentially want an AND gate that you essentially want that to go to the overflow instead. So what you essentially want is a NOT gate here. So this now is it XOR gate you want? Yeah, you want XOR again, don't you? You want double XOR and so if it's yes, you want double XOR. Or will not AND work? No, not AND won't work because not AND will be on if it has no input. So it needs to be XOR. We'll say that the signal is coming in from over here. See something now. Signal comes in from over here, so and you have this signal here. So signal switches it off if that is on, like this. But also it needs to go over to the So this is complicated. Think so. You need this. Oh, interesting. Made a bit of a timing circuit. So this then, oh yes, that was what that was for. Basically, if those are both of those are off, so you need sort of not and that. So what this means is that if this one is on and basically that means that there is an overflow bit added from here, whereas if I then switch Yes, I think that's correct. Let me just switch this one off and make sure that's working. Yes, this should. So this, fundamentally what this does is it takes an overflow bit from a previous order of magnitude of the binary addition. So if you're if you're adding a 8-bit binary number together, for example, what you do is you add so two 8-bit numbers. What you do is you take the first 2 bits, you add those together, and you take the second 2 bits, you add those together, and you take the third 2 bits and you add those together, and so on. But obviously, when you add the first 2 bits together, if you get 2 ones, blow bit, which takes that power of 2 and adds it to the next bit up. So what that means for a binary adder is that for your 2-bit adder, it needs to accept a third bit, which is the overflow bit from the previous order of significance, and then it needs to output what's called the overflow bit, which is not so on. Looks like OBS just disconnected. So yes, basically input 2 bits here, bit from one number, bit from the other. Input an overflow bit. So this is the equivalent. This is the number carried forwards from the previous order of 2. Input that here, and then if the output is greater than the current order of 2, it will output the overflow bit here. Otherwise, it will output the normal bit here. So to add, so 1 plus 1 equals 2, which in binary is 0.02. So we got outflow bit here 1, but also because we got outflow bit input here, we get an extra 1. So this is 1 1 in binary, which is 3. So basically what I'm going to do is I'm going to stack this, and then I'm going to stack another one up here, and then another one up here, and then I get 16 of these, so that I can add 16-bit numbers together. And yes, basically, so this output here will go up to the next layer where it will feed in as this bit here. So this is not exact by any means, just demonstrating the concept to you if you're not familiar with binary adders. Basically, this overflow bit becomes the overflow bit input to the next layer, and like that, it can add arbitrary numbers of bits together. With an arbitrary number of layers. Now, so basically, now that I've got what's the actual best way of stacking this, right? So this is, hang on, was there any point in that? There wasn't, was there? So what's the best way of stacking this? So what will work best is if I have so this goes in line with this, so this will work best. And then if I essentially mirror it over here, and I'm just going to fill up this for neatness. Just so that it looks cleaner. and I think that is filled in correctly. Put one here. That should be correct now. So, yes. Mirror it on this side, basically. Wait, hang on. If I do that, that's problem with doing that is that makes it stepwise. So, that's not. If I instead route it like this, so this comes with a marginal cost in. No, that's going to be. It's actually free because it doesn't involve any more repeaters than it would otherwise, I think. Like repeater here, that's free. Then bridge up here like that. So we need something like this. So that needs to go forwards too. Then down. Comparator on the inside. Like that. Straight to a comparator here, right? So comparator there, and then yes. Yeah, feeds those results into each other, and then it doesn't AND gate on the outside. It goes not like that anyway. Or maybe it is like that. That should work. So then you need the apparatus for the overflow bit, which is gah, my memory's not great. That is interesting. Slightly out of so it should be one more over that way. Why is that? Oh, that's why. Yes, offset by one. No matter. So it goes completely. So it goes sideways 2. One, 2. So that comes up. What comes up though? So it would be that's yes. Oh, hang on. Yes. Of course, that would be problematic. You know what? I can fix this whole mess. And fix him. Right, that's correct. That goes there. So that is then correct. Except it needs the logic over here. The logic over here is that signal from the side switches it off. So it needs to be like this. Like so. This feels so convoluted, it must be wrong. So that's a simple AND plus a, well, a simple OR. So this goes like so. And then it also needs to, is it AND or is it not? Yes, it's not, isn't it? They're not. So you need not this. And there, now that's essentially symmetric. Apologies for my internet. Right, so one more layer on the outside here, it would go. Yes, it goes like so. Hang on a second, is that going to be a problem? Yes, that might be a problem. Because it's gonna, I need to add one more, a gap of one more in there. Basically, it was because I lined it up incorrectly. As I say, you now get to enjoy watching me doing all of this again. It's just one block over. So that's lined up correctly. What you need to do is bring this in here. Put an arch here. No, put an arch here. Actually sure if it matters if there's glass there or not, but stick with the original design. Comparator gate there. should then be correct, and then you have 1 goes down left. Should look like that. So then you need the extra layer here. This is how that works. You go not and that. I believe it's there. Yes. Like this, basically. Oh, there needs to be a back propagation. Hang on, is that completely broken? Oh, so this design is actually slightly broken because there needs to be an AND gate there, and I forgot to put an AND gate in there. Um, fix first and goes a little something like this. So this is XOR, and it turns off if Gosh, this is grossly complicated at this point. So if this is off, that means that there needs to be a bit carried forwards. Either means there's no input to the system, or there needs to be a bit carried forwards. So if this is off and then needs to be a bit carried forwards, it's because this is on, in which case this works. As it was before. Right. Because so yes, that would work. So there's now 3 input bits, so each output should be lit up. That output is lit up. That output is not lit up. Why is that not lit up? That's why. So now that works. Okay, so now imagine there's one. So if I turn one of these off, there should just be the overflow bits lit up. So that's off. That's on. That's correct. Let's try it with the other one. That's on, that's off. Yes, that's also correct. Now let's turn both of them off and the normal bit should be lit up. That's correct. So the logic there is correct. Now if I do that with this one here, because of the error, it's basically, I think if I turn this off, I think the error is that if I turn this off, it stays the overflow. The output should be off now, but it's still on, right? Because I put the NOT gate here. So in this case, it's a relay there. And I believe but it needs to come out. Two more. Oh, now that's a problem. But not one that's difficult to fix. Completely forgetful. Okay, so now that that's done, if I switch this off, and so currently we've got input over here, those both on, which means that the so this is the outflow over here, so that's on, and that's on. Now if I switch this off, the upper one should turn off. No, the upper one stays on because those two are on, but that's fine, that's incorrect. That one turns off. If I turn one of these off, that should leave the outflow still on, that off, yes. Now if I turn this off, now outflow should turn off and this should turn back on. Yes. Now this is the basis for the adder. Just neaten it up a little bit. Just working on the MOSFETs. That's MOS with a double S. I should just be able to copy paste this and stack it. So stack it so this layer sits on here and then it goes up essentially. So to recap, what I've done is I've built an extremely ad hoc, let's say, binary adder that takes as input 2 bits and it adds them together, and it also takes an input of 1 overflow bit, which it will also add, and then it has an overflow bit output that it will send to the next bit. So again, that's because if you have 2 bit addition, and each of those 2 bits is a 1, you need to add another power of 2 to your binary number, and so essentially it needs to accept another power of 2 from the previous power of 2 below it, and then it needs to output another power. It needs to output the overflow to the next level up as well. So it takes 2 bits here and overflow bit here, and it outputs its answer here, and it outputs the overflow bit here. And then I've stacked them in such a way that I can just stack up 16 layers of this basically, and then sum the answers. Well, the answers don't get summed together, but the answers get taken to memory. But